Okay, today we'll start another chapter, functions of complex variable. Actually, it includes limits, continuity and differentiability and analytic function. Today, in this class, we will start with limits, continuity and differentiability with the function of complex variable. Okay, functions of complex variable. The theory of function of a complex variable is of most importance in solving a large number of problems in the field of engineering and science, especially. Many complicated integrals of real functions are solved with the help of functions of complex variable. Now, complex variable. What is complex variable actually? We must know x plus iy is a complex number if x and y are constant. Remember it. But if there are x and y are variables, x is the real variable and y is the imaginary part variable, and including x plus iy will be the complex variable, and it is denoted by z. So complex variable z equals to x plus iy. X is the real part and iy is the imaginary part, where I equals to square root over -1, and this is the Cartesian form. In x-axis real part and in imaginary axis y variable. Okay, so the point x comma y will be denoted by by this diagram, and this diagram is called Cartesian form. You must know about the polar form. If z equals to rn to cos theta plus I sin theta, that means if x equals to r cos theta and y equals to r sin theta, then this present polar form of complex variable. So for this graphical depiction, and the p will be x comma y, this is the Cartesian form, and r comma theta will be in polar form. So angle will be the magnitudes and r will be the argument, modulus. Okay, so x will be the real part and y will be the imaginary part. And we must know another form of complex variables that equals to r into e to the power I theta. This is the actually exponential form. We already discussed in our first class complex number. You must know this is the Cartesian form and this is the actually polar form of complex variable, and this is the exponential form of complex variable. Now, function of a complex variable. What is function of a complex variable? Main question, functions of a complex variable. Suppose f of z is a function of a complex variable z and is denoted by w equals to f of z. Just the representation of a complex number with variables x and y will be called function of a complex variable, and it is denoted by w equals to f of z. It also can be represented as w equals to u plus ib. You must know z can be represented as u plus ib. U is the function of xy and b also function of xy. Remember it. So u is the real part of complex variable and b is the imaginary part of complex variable. Now limit of a function of a complex variable. Let f of z be a single valued function defined at all points in some neighborhood of point z naught. Then the limit of f of z as z approaches z naught is w naught. Mathematically, limit z tends to z naught, f of z equals to w naught. If z tends to z naught, then we get a limit of f of z, which will be approaches to w naught. For example, prove that limit z tends to 1 minus I of z square plus 4z plus 3 divided by z plus 1 equals to 4 minus I. Suppose left hand side is this, z tends to 1 minus I of z square plus 4z plus 3 divided by z plus 1. After factorizing z square plus 4z plus 3, making it middle term, z plus 1 into z plus 3. Z plus 1 cancel. Then we get limit z tends to 1 minus I of z plus 3. This equals to just putting if z equals to 1 minus I, that means that z tends to 1 minus I, putting z equals to 1 minus I here, we get 4 minus I. That means if z tends to 1 minus I, then f of z will be tends to 4 minus I. In another way, we can say if z approaches to 1 minus I, then f of z, this whole f of z will be approaches to 4 minus I. Okay, this is the actually limit of a complex variable as an example. Similarly, what is continuity of a complex variable? The function f of z of a complex variable z is said to be a continuous at a point z naught if for any given positive number epsilon we can find another number del which is also not positive, such that the difference between functional difference between f of z and f of z naught will be, this distance will be less than epsilon. Whenever for all points z of the domain satisfying the point difference z minus z naught, this is the point difference which will be less than del, then f of z is said to be continuous at z equals to z naught if we get the limit z tends to z naught of f of z will be equal to f of z naught. This is the actually mathematical definition of this. In short, we can say if the functional difference, this is the difference between functional difference at points z and z naught. Okay, at z f of z and at z naught the function will be f of z naught. So the difference will be less than epsilon whenever the point difference will be less than del. Satisfying z equals to z naught, the limit will be what? F of z naught. This will be equal. If this equal, satisfying these two conditions, one is functional difference condition, another is point difference conditions for every epsilon and del, which will be must be positive. However small, this will be however small, epsilon and del must be positive. The functional difference, this is the functional difference, and this is the point difference. Point difference will be less than del, then functional difference will be less than epsilon. Satisfying this condition, the function will be said to be continuous at z equals to z naught in a complex function of a complex function. Now, what is differentiability of a complex valued function? Let f of z be a single valued function of a complex variable z, then first derivative of z can be written as the limit del z tends to 0. Del z is very small, which is tends to 0, and this functional difference f of z plus del z minus f of z divided by del z. This difference divided by this ratio of limit will be called differentiability of a complex variable complex function. And this ratio, the limit of this ratio, provided that the limit exists and is independent of the path along which del z tends to 0. Let P be a fixed any point, fixed point, okay, and Q will be another point at z plus dz, okay. P, and this is the complex curve, okay, and this is the first point P, and this is the ending point Q. Now we are if P tends to Q, okay.
হইছে ইব্রাহিম হইছে স্ক্রিন শেয়ার হইছে ভালো করে দেখ
স্যার এখন হইছে
okay. First derivative of z can be written as limit del z tends to 0 whenever this ratio functional difference divided by del z, okay, very small distance del z and the difference between f of z plus del z minus f of z. This limit of this ratio can be denoted by the first derivative of complex function. So and if satisfy this, then we can say that the limit exists and is independent of the path along which del z tends to 0. Suppose P be the starting point and Q be the ending point, Okay, and P be fixed point and Q be a neighboring point also, maybe neighboring point. The point Q may approaches P along straight line or a curved path. Okay, if tends to, if del z tends to 0, if there is no difference of values of z, then there will be no functional difference, this ratio. Okay, whenever del z tends to 0, so we can say that this is the differentiable function. For example, we can say, consider the function f of z equals to 4x plus y plus I into minus x plus 4y. Now to find out the we are discussing to find out the differentiation of f with respect to z, complex variable. Now f of z equals to this, they are given. We can write this into two parts. One is real part and another is imaginary part, u plus ibi types. Okay, first part is u equals to 4x plus y, and second part, imaginary part, b equals to minus x plus 4y. Now f of z plus del z, f of z plus del z, what will be? Just x will be increased. If z is increased to del z, then x will be increased del x and y will be increased del y. So x become del x plus del x and y becomes x, y plus del y, plus I into x plus del x, and y will be increased, y increment y plus del y. Now this difference, functional difference, f of z plus del z minus f of z will be just this value minus this value. Okay, we get this one. Now taking ratio of functional distance, this distance functional difference divided by del z, small length, this ratio can be denoted by this divided by del z, what will be? Del x plus I del y. Okay, so actually by the definition we can write first derivative del f del z equals to this one. Now along real axis means what actually? X-axis, right? Along real axis del y will be what? 0 along real axis, because it is partial differentiation. So partial, if in partial differentiation, if we take the differentiation with respect to x, y will be what? 0. So del y equals to 0 along real axis. So putting del y equals to 0, we get this. Along imaginary axis will be this imaginary axis, then del x will be what? 0. Okay, del x equals to 0, and del z will be what? I del y. Just putting in here. So putting these values in equation 1 in this del f del z, what will be along y axis? 4 minus I. Okay, along the line y equals to mx, that means the straight line passing through the origin, y equals to x. If q taken on a line y equals to x, then z equals to what will be? X plus iy equals to x plus ix. That means y equals to x. This is y. Taking x common, 1 plus I into x. Now del z, what will be? 1 plus I del x. Del y and del x same. So on putting the value, all these values in equation 1, del f del z along the line y equals to x will be this difference divided by this del x plus I del x. Just putting these values, we get 4 minus I. In all the three different paths approaching q from p, we get the same values del f by del z equals to what? 4 minus I. In such a case, the function is said to be differentiable at a point z in the given region. That means we have proved in different paths along x-axis, same values 4 minus I, along y-axis, same values 4 minus I, along the straight line passing through the origin, that means along the line PQ, y equals to x, same values. Okay, so all values are same for this function. Okay, example 2, if f of z equals to a complex function x cube y into y minus ix divided by x to the power 6 plus y square, when z does not equals to 0, and f of z will be 0 if z equals to 0, then discuss del f del z at z equals to 0. We have to find out this differentiation with respect to z. Now if z tends to 0 along the radius vector y equals to mx, y equals to mx means you must know the equation which passes through the origin, you must know y equals to mx. So limit z tends to 0, f of z minus f of 0 divided by z, what will be? Functional difference divided by point difference. Okay, point difference. This is the point difference and this is the functional difference at z tends to 0, when z tends to 0. So this is the functional value f of z, f of z, and f of 0 what will be? Only 0. F of 0 what? 0 when z equals to 0, and z equals to x plus iy. Now limit z tends to 0, just this, taking this, and this will be what? X plus iy. Limit z tends to 0, minus I x cube y, x plus iy will be what? Cancelled. Then we get minus I x cube y, x to the power 6 plus y square. Now if y equals to mx, putting putting y equals to mx here, then we get limit x tends to 0, minus I mx square, x to the power 4 plus m square equals to 0. But along y equals to x cube, y equals to what? X cube. Functional difference divided by point difference, and this limit will be limit z tends to 0, minus I x cube y divided by x to the power 6 plus y square. This equals to limit x tends to 0, just putting y equals to x cube, we get minus I by 2. In different paths we get different values of del f del z. Okay, df dz. First differentiation of f with respect to z, that is 0 and minus I by 2. In such a case the function is not differentiable at z equals to 0, because this value is different. Okay, minus I by 2 and this 0. Okay, different value we got. This is why it is not differentiable. Most important theorem: continuity is a necessary condition but not sufficient condition for the existence of a finite derivative. Okay, so if any function, even any complex function is continuous, then it will be must be differentiable. Okay, but if it is differentiable, then it may not be a continuous. Okay, now we have the functional difference f of z naught plus del z minus f of z naught equals to del z. We can write this, del z divided by del z will be what? Cancelled. Same functional difference. So just this is equation number 1. Now taking limit on both sides, as del z tends to 0, we get limit del z tends to 0, this functional difference, this equals to, and this will be what? 0 into f of del z. Limit del z tends to 0, this functional difference will be what? 0. This is the differentiation, first differentiation, right? Del z equals to what? 0. And this is what? First differentiation, f dash z, z naught, by the definition of differentiable of a complex variable. Now limit del z tends to 0, functional difference equals to this multiplication what? 0. So limit del z tends to 0, this difference will be 0, because del z equals to what? 0, tends to 0, this is why. So and this will be limit z tends to z naught, this functional difference will be 0. So limit z tends to z naught, f of z will be what? F of z naught. This can be said that f of z is continuous at z equals to z naught. But the converse of the above theorem is not true. Remember it. Converse means what? Actually, if it is differentiable, then it may not continuous at z equals to z naught. This can be shown by the following example. Suppose prove that the function f of z equals to absolute value of z square is continuous everywhere, but nowhere differentiable except at the origin. Okay, origin means 0, 0, 0 point. We are given f of z equals to z absolute value of z square. This is the actually modulus, can be written as square root over x square plus y square. You must know the complex form, polar form of a complex number x equals to r cos theta, y equals to r sin theta, then we can write modulus equals to square root over x square plus y square. That means square modulus square equals to x square plus y square, taking square on both sides. Since x square and y square are polynomial, so this is continuous everywhere. Therefore, this is also continuous everywhere. Now we have first derivative equals to what? Limit del z tends to 0, functional difference divided by point difference. Okay, this difference ratio. Now first derivative this equals to just putting the values of f of z plus del z will be what? Z plus del z whole square, and f of z equals to what? Z square, and del z will be same, and z bar, that means z into complex conjugate of z will be what? Absolute value of z whole square, that means modulus z whole square. So limit del z tends to 0, we can write this square using this identity z plus del z and conjugate of this z bar plus del z bar minus z square can be modulus square can be written as z bar using this identity del z. Now just multiplying we get this, and z bar will be cancelled, we get this divided by del z. So limit del z tends to 0, and z bar plus del z bar plus z into del z bar divided by del z. Okay, just dividing with this del z common. Okay, so del z divided by del z will be cancelled from this. Now this can be written as putting since del z tends to 0, so we can write this one z bar plus z into del z by del z. Now if del z tends to 0 and del z bar also 0, conjugate of complex number also tends to 0. Now let us consider del z equals to r cos theta plus I sin theta, where x equals to r cos theta and y equals to r sin theta. Polar form. Complex conjugate will be just minus. Complex conjugate will be what? Just putting minus z bar. Now del z bar divided by del z will be just this divided by this. RR will be cancelled. And similarly, this can be written as cos theta plus minus I sin theta, cos theta plus I sin theta to the power minus 1. So del z equals to cos theta minus I sin theta, cos theta minus I sin theta by de Moivre's theorem. You must know cos theta plus I sin theta to the power something can be written as by de Moivre's theorem cos minus theta plus minus cos minus theta plus I into sin minus theta. Sin minus theta equals to what? Minus sin theta. This is why these are the same. Cos theta plus I sin theta whole square. So del z bar divided by del z equals to cos twice theta. Cos theta by again applying de Moivre's theorem. Cos twice theta minus 2 sin twice theta. So since del z bar divided by del z depends on theta in polar form, okay, depending on theta, it means that for different values of angle theta, del z bar divided by del z has different values. This ratio also has different values depending on different values of theta. So it means that this ratio has different values of for different values of z. Therefore, this limit of del z bar divided by del z does not tends to a unique limit z equals when z equal doesn't equals to 0, because for different values of this ratio we get different values of z. Okay, so it has no unique limit. Thus from equation 1 it follows that first derivative of f z is not unique and hence f of z is not differentiable when z doesn't equals to 0, but when z equals to 0 first derivative equals to 0 and it will be unique. So the function is differentiable at z equals to 0, but when z doesn't equals to 0 it is not differentiable. So this is very nice example and very important example for you. Okay, thank you. Thanks to everybody. Actually, today we have learned a lot about function of complex variable, especially definition of limits, definition of continuity, and definition of differentiability of a complex variable. And we have studied different kinds of examples, including limits, continuity, and differentiability. Okay, thanks to everybody. Best of luck to everybody.
আসসালামু আলাইকুম।